Today we are going to be learning about the wash method. First, here's a quick overview of the dis method. And what the dis method basically says is that the volume of this entire figure is equal to pi times the integral from b to a times r of x squared or f of x squared. And that basically means let's say we're at f of a and we want to find the area of the circle. If you were to revolve f of a around the x-axis, that would just be f pi f of a squared. And basically, to find the volume of this entire 3D figure, you're just adding up all of these individual circles at every single minute point between B and A. And that just gives you your volume. It's pretty simple. But the wash method, it adds in another layer. It adds in another curve. You have your original outside curve, f of x, or r of x. But then you have another inside curve, another inside radius. We'll call this g of x, or lowercase r of x. And basically, using the wash method, we are finding this volume. Which basically means that we're finding the volume of this entire figurine minus this little small piece. And how do you do that? It's pretty simple. It's basically the same thing as this method. So you're doing pi b of a, then you can do r of x squared minus lowercase r of x squared dx, and that's pretty simple. To better imagine it, we can think of it as a circle, or two circles rather. Boom. That basically represents the circle created by r of x rotated around the x-axis. But then we have this piece that you are going to remove, or I guess, you're basically, imagine this red area is removed. And so you're just going to find this area. And then you're just going to add it up from here to here. You're going to find up all of these. And that gives you your volume, minus this little bowl area. So pretty simple. Find the volume when the region is rotated about the x-axis. So if you look above, we have these, and we have two radiuses. This is going to be your big r of x, and this is going to be your lowercase r of x. So if you imagine it rotated across, it's going to be like something like this. Ooh, that's not good, but you get the idea. It's going to look something like that. And if we just do our skeleton pattern that we learned before, it's going to be pi from 1 to 0. Remember, this is going to be r of x. This is lowercase r of x. So it's going to be root x. It's going to be squared. That's just going to simplify to x minus x to the fourth dx. Just like that. And once we actually solve this, we're going to get diagonal x minus to the fourth dx. And then integrate, it's going to be x squared over 2 minus x to the fifth over 5, 0, and it's just going to be 1 half minus 1/5, and then since it's just 0, that's going to equal 0, so we can just move on from here. And then, so it's going to be 3 pi over 10. And one thing I forgot to mention is there's this nifty little tool called GeoGebra, and that's really helpful when visualizing these animations. So just click on, we already have the equations put in, and let's just play it. Yeah, you see how it just rotates around, creates that nice shape. Very cool. And we basically have the same question as before. same graphs, except the question is asking when the region is rotated about the y-axis. And so when this happens, you basically want to convert these two equations into equations that are in terms of y. So how do you do that? It's pretty simple. You just do square these, x equals y squared, and then x equals root y. So it's basically like it is basically like the same thing as these two equations, just switched around. And and it's in terms of the y-axis. So when we were talking about in terms of the x-axis, when it was rotating basically like this. But now that we're rotating in terms of the y-axis, it's going to look something. It's going to look something like this. Yeah. Okay. And so it's basically going to be the same thing. Remember, always pi in the front. Integral from lower bound is 0, upper bound is 1. Remember, they still intersect. The y coordinate is 1. So, and then outer curve is the root y, and then the lower curve is y squared dy, and it's just going to equal the same thing. It's still going to equal 0.942. So this equation is a bit different because this time we're rotating around the line x equals 3 instead of an axis like the y-axis or the x-axis. But if you notice, this is pretty similar to just the y-axis. So to basically solve any of the y-axis problems, we just have to convert these curves into terms of y. So x equals y squared and x equals y. Pretty simple. And okay, so the main thing we want to figure out is basically build in this line that we're revolving around, or build in like an offset to this line, is determine, for example, for this curve, we want to determine what's this distance equal to. So how do we do that? It's pretty simple. We just do 3 minus 1y. Very simple. And then for this one, it's just the same thing, but it's 3 minus y squared. Because basically, you are taking in this value and you're subtracting this amount from 3 and you get this. Pretty simple. So if we just build our skeleton, it's going to be 1, 0, and then it's going to be 3 minus y squared minus 3 minus y squared dy. Yeah, and once we solve it, we get an answer of 5.341. So that is the volume when the region is rotated about the line of x equals 3. And you can just see our equation right here. It's the same one that we had before. So find the volume when the region is rotated about the line y equals 2. It's going to be the same process as before. However, if you think about it, it's basically the same thing as with respect to the x-axis. So we're going to have to, except it's up 2, obviously. So we're going to have to be in terms of x. So right now, how it is perfect. So let's just set up our skeleton. 0, 1, 1, 0. And then we have, so when we actually solve it, we get an answer of 3.246. As you can see here, it's the same thing as before. But yeah, and that is the volume when the region is rotated about the line y equals 2. Yeah, so that about wraps it up. So enjoy your newfound washer method abilities, Eganites.